Okay. Enough of that. You know, it's time for Mr. Pete Madreski to tell us why are minerals so complicated?
Well, okay. And I guess I can jump right in and start sharing my screen and talking about this.
Yes, sir.
Nice of you all to be willing to listen.
Oh, yeah.
And you seeing that okay?
Yep. Yeah.
My title, like I said earlier, didn't scare people away too much from listening. And the point of my talk as well is going to be to try to inform you all a little bit about maybe some things about mineralogy that you might not quite know or not quite understand. And but my bottom line is going to be it really doesn't have to be that complicated after all, but I'm going to kind of try to explain some of the complexities. And I'll just say that as a matter of fact, what was part of the inspiration for me to want to present this program to you is I realized I was responsible for signing up the speakers for the year, and January was coming up on me much closer than I realized. You know, I'm not good at looking at calendars. And rather than trying to run around and talk some speaker into presenting to us at the last minute, I thought I'd give this prepare this presentation that I had in mind. And one of the reasons I had it in mind actually relates back to something we were chatting about at the beginning of the meeting today. We were talking about the picture I showed to Beth and some others about a fossil log with what looked like two bird holes in it in Cerrillos, New Mexico, at their the turquoise shop and mining museum that these folks have, which is where I saw the log with the bird hole. And so in the course of looking at the Cerrillos turquoise that they had there, a couple of weeks later, we were having a chat with Ray DeMark from New Mexico, old friend of mine, who many of you know, and talking about Cerrillos turquoise. And Ray made a comment that kind of an offhand way is, you know, a lot of what's sold of the supposed bona fide turquoise that's sold as turquoise really isn't turquoise after all. And that is going to be one of the slides in my show. One of those things that illustrates how complex minerals can be these days, because scientists and mineralogists are getting so precise and so nitty-gritty about what distinguishes one mineral from another. And it is indeed true that a lot of some turquoise that you see, well, some turquoise, of course, that you see isn't turquoise at all. It's something else that's either been dyed or is a similar color, like howlite, which is dyed, or chrysocolla, which is a different mineral. But then there's turquoise, and then there's turquoise, and so that's going to come a little later in my talk. But that was kind of the inspiration for this, okay? And so maybe some of you have or have not ever thought that, gosh, minerals do seem awfully complicated these days. Maybe you don't think that's true, or maybe you just think they're complicated, period, and you'll stick with the simple basics. But let's see what I can share with you and maybe raise your understanding and consciousness a little bit. And in my pictures here, I'm kind of taking the theme that when most of us first learn about minerals, okay, things seem fairly simple and straightforward. And like, here's pyrite. Do you see my cursor when I move it around, by the way?
Yes.
Yes. Yeah.
Okay, good. You know, pyrite is a fairly simple mineral. It has a cubic crystal structure, has a fairly simple chemical formula, and basically pyrite is pyrite. You see pyrite and you know it's pyrite. It has distinctive properties, and there really isn't anything else gets confused with. I mean, it might resemble some things, but fairly simple. I thought I'd throw one on as a contrast. It wasn't the one I mentioned in the club newsletter, where I mentioned a mineral name that was sort of in the same group, and it was, I forget what I said, plumbohydroxy something something pyrochlor. I turned out that's not very photogenic, so I picked a related mineral that's a little more photogenic. Some nice dark red octahedral type crystal, has a name that goes on, which might intimidate some people to pronounce, and it has a chemical formula that goes on too. And when you look at things like that, it's like, yeah, minerals are really complicated. Do mineralogists just do that on purpose to confuse people? So that's what I'm going to try to share with you. I'm showing a book, actually one of my favorite field guides on minerals. There have been different versions of this Golden Nature Guide series book, and you read that and it makes things sound fairly simple. Of course, most of the material in that book was written quite a few decades ago, but I still think it's a great book. And I'm going to finish up with a picture of this book too. It's really the one that I recommend to beginners more than anything else, because it really teaches you a lot about minerals and rocks in a fairly simple way. But let me start going through some minerals here that you will all know and recognize and love. Okay, well, first, a little bit about what is a mineral, okay? And this is part of what I always cover when I do the annual program for beginners or whoever at the Denver show about starting a mineral collection. So the simple definition is just that a mineral is a naturally occurring inorganic solid crystalline substance. It's pretty straightforward. We're not going to debate all the subtleties about this. And of course, it can be, since that's the two types of chemical substances that can exist. It can either be a single native element or it can be a chemical compound. And there's examples of three fairly simple, one metallic element, two chemical compounds that are minerals. And there are lots of minerals. And I always tell people, if you get a book like The Golden Nature Guide to Minerals, and you get one of the old ones that was published 20 or 30 or 40 years ago, it may say that there are over 3,000 minerals or 2,000 minerals, while in actual fact, there are over 5,000 now. And a few years ago, they made a big deal out of the fact that they had exceeded a count of 5,000 different minerals. And as of last time I prepared a slideshow at the Denver show, there were 5,512, and I looked it up a couple days ago on Mindat, which of course is a great website resource for anything you want to know about any mineral. And now it's up to 5,663. So as I say there are generally on the order of 100 new minerals described every year. And just as an aside here, which we'll kind of little bit come to later on too, since it's the two different things distinguish each mineral from all the others. Its chemical composition and its crystal structure. So you can have minerals like graphite and diamond that are both minerals, have exactly the same chemical composition, pure carbon, but have a completely different crystal structure, which ends up making them have completely different physical properties, etc. And then another example is calcium carbonate, very common material, which can either be the mineral calcite or the mineral aragonite, which look quite different and have different crystal structures, and which causes them to have different densities and different refractive indices and everything else. So that's the basics of what minerals are. Okay, so now we're just going to look at some of our favorite, perhaps, and simple minerals. And so I'm going to make it sound real easy at the beginning. So halite, sodium chloride, is a very common mineral. It happens to have one of the simplest crystal structures of all minerals, where the sodium and chloride ions are arranged in a simple cubic arrangement where they alternate positions. Those are just two different perspective views of a drawing or a model of the sodium and chloride ions in sodium chloride, okay? So that's pretty straightforward. And once again, it's a simple mineral. NaCl, the mineral name is halite. It's basically what it is, okay? Just for the record, as many of you know, the proper name for the crystal system that these, quote, cubic minerals are in is the isometric crystal system, which means that the dimensions of the unit cell of each part of the crystal are the same in all three up, down, and sideways directions. So rather than saying cubic crystal system, that's why I say isometric in all these slides, at least I think I do. You can have isometric minerals in the isometric system that have a cubic crystal shape, or they can have an octahedral shape and some others, but they're still in the isometric crystal system. So that's a big word. Cubic's easier, but isometric's more popular. So we'll look at a few more common favorite minerals. Pretty simple. Fluorite, once again, forms cubic crystal shapes or octahedrons. Pretty simple chemical formula, and fluorite is just fluorite. And one could say there's nothing further to say about it. And pyrite is likewise that I started out with. Here's some photos that illustrate how you can have cubic pyrite crystals, or you can have octahedral pyrite crystals, four-sided double pyramids. But again, pyrite is, straightforward. You look at any book about minerals, you learn what pyrite is, you learn what its chemical formula is, its crystal shape, its hardness, and you kind of know pyrite. And pretty much the same for quartz. Fairly simple chemical formula, very distinctive properties, not too much you can confuse it with. Let me just make one more aside, and that's the last technical aside about crystal structures that I'm going to mention, okay? There's a little bit of confusion about how you're properly supposed to describe the crystal system that quartz belongs to, okay? This, I will admit, causes great confusion to me periodically, and I have to go back and look this up, because we normally say that there are 6 crystal systems, starting with cubic is the most symmetrical, triclinic is the least symmetrical, and one of them is hexagonal, which basically means 6-sided crystals, and that's simple. But they also have what they call the trigonal group of crystal structures, and a few minerals that are hexagonal are simply purely hexagonal, and the crystals will have 6 sides, and there are actually only a few minerals like that. They have what we call 6-fold symmetry. Beryl is one of them, apatite is another one, but most of the minerals that we think of as hexagonal actually don't, if the crystal is perfectly developed, don't really have complete 6-fold symmetry. They have some other little extra crystal faces appear, and they belong to the trigonal class of minerals, which is considered a subset of the hexagonal set, where they actually have only 3-fold symmetry instead of 6. And quartz is like that. So quartz isn't completely hexagonal. It's really in the trigonal group, and so is calcite, and so are a lot of minerals that we think of as being hexagonal. So is corundum. So I'm just gonna, that was my aside. I'll just pass that on, okay? So quartz, now quartz is, of course, since it's such a common mineral and it's such an attractive mineral, and it has the neat thing that it comes in so many different appearances and colors and varieties. So the bottom line is, and of course, I think you all know this, is that we talk about varieties of a particular mineral, and often those refer to gemstone varieties that are different colors and that are given a different name when they're used as gemstones. They're still the same minerals, and usually the color difference in these minerals, like what makes amethyst purple, is due to very tiny amounts of impurities, like parts per million, as in the purple color of amethyst. So as you know, we have a lot of different varieties of quartz that we all know and love. Amethyst, rose quartz, blue quartz. One that you don't see very much is green quartz, that's traditionally called praise. That's more a word that was used in the old days. And when we talk about true green quartz, we're really talking about not quartz that's just due to inclusions of some green mineral, making it cloudy and green, but where the quartz itself would be green. That's pretty rare. And most of you know that there's also a whole family of varieties of quartz that we call cryptocrystalline quartz, where instead of the quartz being in large crystals, macroscopic crystals, it's a very microscopic scale intergrowth of tiny, usually fibrous crystal needles. And this photo here is a photo of a polished section taken in polarized light of a piece of chalcedony. And you can see how each little different colored fiber in there is a different individual little tiny crystallite of quartz. The cryptocrystalline means hidden crystals, means they're so small you can't see them with your eye. So agate and its related things, chalcedony, jasper, chert, are all different varieties of cryptocrystalline quartz. So quartz, it's simple in that we got one mineral, but there's a lot of varieties, but they're easy to understand, okay? Got a few more that are pretty simple. Copper is won't say it's our favorite native element, but one of the most common ones. Sometimes occurs in crystals, sometimes just in masses or sheets. And again, copper is a mineral. It's a naturally occurring crystalline form of the element copper. As a bonus, in the one picture, it's what they call half-breed nuggets of copper and silver together. And silver, again, is its own mineral, nearly pure silver. Also, when it forms crystals, which you don't always see, it's in the isometric crystal system too. Just because copper minerals are kind of fun, I threw in a few more. And again, simple, straightforward. It would, you would not be intimidated by anything I've shown you so far in learning about minerals, because it's all pretty straightforward. We know that there's a sulfide mineral that looks somewhat like pyrite, but it's kind of a deeper yellow. It tarnishes more easily. That's chalcopyrite. It contains copper as well as iron. It's in the tetragonal crystal system rather than isometric, but it's still an easily understandable mineral. And here's a couple more, and they're pretty too. This is one of my favorite minerals because I think everyone likes deep red minerals. Cuprite is copper oxide, forms usually octahedral crystals, sometimes cubes, so it's in the isometric system. Pretty straightforward. It's not related to any other particular mineral. Couple more. Everybody knows and loves malachite, which is a copper carbonate. And it's its own mineral, and then its related mineral is azurite, which is also a copper carbonate. And to really understand the difference, other than the color, you kind of have to switch back and forth and look closely at the chemical formulas, and you see azurite, we got 3 copper atoms and 2 carbonate groups and 2 hydroxyls. And in malachite, it's 2 and 1 and 2 instead of 3 and 2 and 2. So a different proportion of carbonate and hydroxyl in it, but each of them is a good mineral and well behaved and everything else. I'll show you one more, dioptase, a very beautiful, often nicely crystallized, found in places like Sumeb in Namibia, kind of a distinctive, slightly bluish green color. It's another copper mineral, hydrated copper silicate in the trigonal crystal system, same as quartz. So that's another good mineral. So let's see if we're brave enough to start getting a little more complicated. Okay. So now we got two things going on here. These are a lot of popular minerals, the carbonates, okay, which includes calcite, which everyone knows. But here, two things. You can change the crystal structure and you can substitute different metals for the calcium and calcium carbonate. So we end up with a whole family of minerals here. So the ones on the left, the rhombohedral minerals, all have basically the same crystal structure. They have very good cleavage, and they cleave into the angular pieces that we call rhombs or rhombohedrons, okay? And of course, in addition to calcite, probably the best known one is rhodochrosite, which is our state mineral, where we got manganese instead of calcium. And the chemical element manganese, which usually colors things red or pink, gives it its red color. Couple less known, if it's iron instead of calcium, we have siderite, and magnesium instead of calcium, it's magnesite. Jumping over to the right side, we can have not all, but some of those same chemical elements, particularly calcium, in a completely different crystal structure. And the crystals look different. And aragonite is the one we usually mention, usually occurs as sprays or needles of crystals. The picture that I pasted in here is actually not aragonite, but it's strontianite, which has the same structure as aragonite, but it happens to be the less common element strontium instead of calcium. And then we can have a barium mineral, witherite, and a lead carbonate, cerussite. So they're all in that same aragonite crystal structure family. And then going back and looking at our chemical formulas for the carbonates on the left, we have a family of carbonates where there are two metals present instead of just one. So here we've got written the formula with two carbonate groups and one atom each of two different metals, metals. So dolomite is probably the best known one, where you got calcium and magnesium instead of just pure one or the other. There's an iron bearing carbonate called anchorite, calcium and iron. It's usually brownish. There's one that's mostly known from South Africa and from Franklin, New Jersey, where it's got calcium and manganese, and it's kind of a nice pink color, not as deep red as rhodochrosite, because it's only got half as much manganese. So now we're looking at a family of minerals that varies both by its crystal structure and its chemical composition. So things are a little bit more complicated, but still manageable, okay? One thing I like to say is that one of the good things that minerals occur in these families that are related by slight but significant differences in their chemistry is it helps you to learn about minerals, because you don't have to learn about 5,500 totally separate, unrelated minerals. A lot of these are grouped together in families. So if you kind of learn some things about one of them, like calcite, it helps you understand the whole family. So I would count that as a good thing. Let's see what I came up with next. Another favorite mineral. And by the way, if anyone would like to ask a real good, I mean, any kind of a question or a comment, I welcome you to just chime, because there's not that many of us here. Just break right in and ask me. Don't be afraid to, okay? So the olivine is, many of us know that olivine is a green mineral. It occurs as a gemstone that we call peridot. We know that it is actually an extremely common mineral on planet Earth because it's what makes up most of the Earth's mantle. So even though it's deep down and we don't see it, there's an awful lot of olivine underneath our feet. And of course, it occurs in lava flows. And it starts getting a little confusing because there's so many different names for this. So to a geologist and a mineralogist, olivine is the main name we refer to it. And peridot is just a gemstone name, okay? Refers to the same thing. But olivine has a chemical composition that can vary completely between two different metals. It contains both magnesium and iron, and it can be almost all magnesium or almost all iron, or sometimes somewhere in between. And so since the magnesium form and the iron form are really two different minerals, and they have a different ideal formula, they each have a name. So the magnesium-rich form of olivine is called forsterite. It's named after somebody named Forster, and I can't say I remember who that was. And the iron-rich one is called phaolite. Now, forsterite is a whole lot more common. And basically all the olivine you see and all the peridot you see is all forsterite, okay? Phaolite actually only occurs like this this photo I showed down here. You usually find it as microcrystals that formed in little cavities with other minerals in either in lava or in some kind of hydrothermal hot water deposits. And it's usually brown rather than green. It's the iron in the peridot or in the olivine that gives it its green color. If it were completely pure magnesium and had no iron at all, it would be colorless. But pretty much most natural olivine has enough iron to give it its nice distinctive green color. And there happens to be another one in that family, which again is a manganese one. And mostly you only encounter this if you're a real lover of those Franklin, New Jersey rare minerals, okay? Tephra is found there, doesn't look like much. But one of the things that gets tricky is when you look up a lot of databases about minerals, there have always, in geology and mineralogy and maybe some other sciences, there have been people who like to lump things together into convenient groups, and there are scientists who like to divide them up into as many pigeonhole categories as possible. So a lot of the feeling among really picky mineralogists these days is that we should only use the mineral names that refer to the exact specific mineral species. So forsterite is magnesium silicate. So if your mineral has mostly magnesium in it, they say you should only be calling it forsterite. And if it's mostly iron, you should always call it phaolite. And you really don't ever need to use that general term for the whole group, which is olivine. And so there are some who would just say olivine is a superfluous word and we don't need to use it. And that's the reason, what I was coming to, in a lot of mineral databases, you try to look up olivine and it's not there. It's not even listed. You have to know that you have to go to look up forsterite and phaolite. Now, some of us old timers kind of think that's going too far, because most people who study geology or who have ever studied geology in their life know what olivine is, and it means something to us. And forsterite is definitely not a household word. But so that's the story on that. Now you know all about the olivine minerals, right? So let's go to another one. So this isn't the fault of mineralogists trying to make things complicated. It's just the nature of the minerals themselves. And some mineral groups are simply pretty complicated because you can have a lot of ways that they vary, both in their chemical composition and the crystal structure. And the feldspars are one of these. So feldspars are a whole group of minerals, and there are a lot of different kinds of feldspar. And I haven't listed them all here. And of course, you better memorize everything that's on this slide because it'll be on the test at the end of my talk, right? Joking a little bit. So you probably know that there are a group of feldspar minerals that are potassium aluminum silicates. Okay, they're aside from aluminum and silicon, which they all contain, they're richest in the element potassium. And geologists like to refer to those as K feldspars. But then there are different types of that K feldspar depending on the temperature that that feldspar crystallized at and how quickly it cooled. So that microcline is the type of potassium feldspar that we mostly find in granites and pegmatites. It basically cooled the most slowly and formed at the lowest temperature. And orthoclase has a slightly different crystal appearance. It's monoclinic instead of triclinic, and it forms in igneous rocks that formed at a little higher temperature and cooled a little quicker. And then, by the way, there is an error in my slide, if you can believe it. There's supposed to be an aluminum in each of those formulas, so I left out the Al and sanidine. So sanidine is one that forms in really hot volcanic rocks that cooled very quickly. And some sanidine, and it has a relation to the fact that it cooled quickly, cooled rapidly, will have this silvery iridescence, and we call it moonstone. So we'd say the moonstone is a gemstone variety of sanidine, but each of those three are different minerals. Okay, everybody with me? And then you probably know, and some of this is just a little complex, but you have to live with it. There's also feldspars that, instead of containing mostly potassium, are rich in either sodium, calcium, or the combination of the two. And one of those is albite, and the calcium-rich feldspar is called anorthite. So those are considered two separate minerals too. And in my picture up here, this is one from one of the pegmatites in the Pikes Peak area. And I bet you know that the nice blue crystals, of course, are amazonite, which is a variety of microcline feldspar. It's simply microcline that contains the right trace elements, gives it a blue or greenish color. And then the white bladed mineral with it is albite. Often has a completely different crystal appearance. Albite is usually pure white as opposed to microcline, which, if it's not blue, is often kind of a buff tan color because it usually has a little bit of iron in it. So there's our potassium feldspar, the amazonite crystals, and the albite, which is white. And then there's a whole series, a complete series in composition, all the way from albite to anorthite. And in the old days, mineralogists gave names to those different intermediate compositions. And that's one of those groups of names that the purists nowadays say they're unnecessary, because we got albite and we got anorthite. That's two different minerals. And one has sodium and one has calcium, and there's no need for all those other stupid names like labradorite. But most geologists still use them. And of course, labradorite is feldspar that kind of falls in the middle of that sodium calcium spectrum, okay? And not all labradorite is beautiful like this one. To a rockhound or a gemstone person, when we say labradorite, we think about it has what we call a schiller. It's got this iridescent, ranges anywhere from gold to blue to orange to silvery effect. It has to do with the cooling of the feldspar crystal structure. So there's a lot of labradorite that is just gray feldspar and doesn't look pretty, but the part that does look pretty and is polished and used as gem material is simply also called labradorite. We don't have another name for it. So let me move on to another group of minerals. If my button allows me to, let's see. There we go. So here's a simpler mineral again. Ruby. Corundum. Corundum's the name of the mineral. It's aluminum oxide, fairly pure. Once again, it's in that trigonal subdivision of the hexagonal crystal system, just like quartz is. And here, it's really pretty simple. It's just one mineral. And due to the trace elements in it, it comes in a number of different colors. And traditionally, since ancient history, the deep red corundum, hardness of 9 is all of these, we call ruby. And any other color of gem corundum is all considered sapphire. A lot of us think of sapphire as usually being blue, but you probably know it can be pink, purple, green, yellow, orange, anything in between. If we've simply got corundum that is cloudy and gray and ugly, or it's just colorless, sometimes the colorless material would be also known as sapphire, but basically it's just the mineral name corundum. So that's easy. And beryl is a little bit of the same thing. It's one single mineral, contains beryllium. So it's beryllium aluminum silicate. It's a hexagonal mineral. And with the exception of what I'm coming to at the bottom here, it's one single mineral and it just comes in different colors. And so we've given it traditional gemstone names. And this photo that I pasted in has a lot of these beryl varieties here. Here's aquamarine, here's morganite, the pink beryl named after J.P. Morgan. Here's yellow. Sometimes it's not a pure yellow. They kind of let a greenish yellow get by. That's called heliodor. I don't actually see a bona fide emerald in here. I don't think this big one would quite count as emerald, but to qualify as emerald, our beryl has to be a real intense deep green, and there has to be evidence from spectroscopy that it really contains chromium or vanadium, which are the metals that color it deep green. And beryl, when it's just plain old green, there really isn't, that I know of, a special gem name for it. We just call it beryl. There are ways to heat treat beryl to remove the green color and make it more like aquamarine. And you probably know that there's a particularly prized and valuable type of rare beryl that is red that mainly occurs in Utah, in the Wawa Mountains. And there's always been a challenge as to what to call that. Now, it's not a different mineral. It's not a separate mineral because it's still beryl with the trace of something, which happens to be manganese in it. There was a name coined for it in the old days, Bixbyite, which was named after a fellow named Bixby, but that never really caught on, and it's not a very pleasing name. And a lot of the gemstone dealers will call it red emerald, which causes a lot of mineralogists to throw up their hands and say, that's ridiculous, emerald is green, let's not have red emerald. But I don't know, you people who do gemstones, what does the red beryl, or does it just get called red beryl? Any comment on that?
That's all I've ever seen it called, Pete, is red emerald. And it just seems to be more of a marketing thing.
Yeah. So then
Pete,
Yeah.
is Bixby, is that named after the same person, that Bixbyite is named?
Yeah,
Okay.
yes, it is. There's a separate mineral, which is a black oxide mineral called Bixbyite. And I think his name was Maynard Bixby,
Okay.
wasn't he? He was a prospector who did a lot of mining out there. And so Bixbyite and Bixbyite were named after him. But, like Bixbyite, it just doesn't attract you to want to buy gemstones of it, okay? So then, jumping on, so just like with the feldspars, there is a group of minerals that are like beryl, have the same crystal structure. These are not household names, but they have different chemical elements substituting in them. And there are actually 6 of them total, and I listed 3, which I at least can relate to a little bit. The other 3 names are really obscure. You can look them up if you want. Turns out bazite, interesting name, has the rare element related to the rare earth element scandium instead of aluminum. And that's interesting. And maybe some of you know, do anybody here know where bazite occurs in Colorado?
No.
It occurs on Mount Antero along with the aquamarine.
Really?
And it's very rare. It occurs in very tiny crystals. People were finding some little tiny crystals that look like beryl, but they were a real deep blue. For a tiny microcrystal, they were fairly dark blue. And when some chemical analysis was done of that, it turned out it was rich in this other element, scandium. So it's a whole separate mineral. And it does occur in Colorado. It's a very rare thing to have a sample of it. But some of the collectors on Mount Antero who carefully look at their micromaterial have found some of that. And there's this other one, Pizzataite, was named after a well-known mineralogist and gemologist, I believe it's Federico Pizzata from Italy, and that was discovered fairly recently. And again, it's in the beryl crystal family, but it has a couple of different extra elements in it, cesium and lithium. That was kind of a neat thing when they were able to name this after Federico Pizzata. So there you go. And I'm not going to bore you with the other 3 names. So let's see what other mineral groups can I still play around with here. Garnet, I wouldn't, so garnet, so I would consider I'm still now in the mineral families that are sort of intermediately complicated. There's a little bit of complexity, but it's usually not that hard to wrap your mind around it, okay? And you probably know that garnet is considered a group of minerals, not a single kind of mineral, because there are different kinds of garnets that have different chemical elements in them, okay? And the most common one, like what we see in most metamorphic rocks, what you get great big crystals of over at the Sedalia mine near Salida, is almandine garnet, which contains iron and aluminum. Most of the gem quality garnet, because a lot of almandine first isn't all very gemmy, very clear, and it's so dark, it's usually a dark brownish red and not really that pretty. But pyrope garnet, which mostly occurs in rocks like kimberlites along with diamond, is mostly magnesium, and it only contains a little bit of iron or chromium to color it. And it's actually what the traditional gem garnets are made of. Bohemian garnet from the Czech Republic is pyrope garnet. And you're probably familiar with some of these others. Spessartine occurs in pegmatites. It's usually orange. Andradite and grossular occur in metamorphic rocks. Grossular means gooseberry. And uvarovite is a deep emerald green garnet, very rich in chromium. So those 6 are sort of the classic garnet minerals. And of course, these are a variety of faceted garnets down here that represent some of those colors. But just like the feldspars and some others, there's actually a big group of garnet minerals. And so there's 8 more that are closely related and 14 more beyond that that are a little less closely related. And most of these are things that most people, if you're not a mineralogist, haven't heard of. Now, there are also more gem varieties of garnet than I haven't listed some of those names here, but you're probably familiar with them. There's demantoid garnet, which is another green chromium-bearing garnet. Somebody else want to name another garnet gem variety that I've neglected?
I think hessonite is another one, isn't it? It's orange.
Hessonite is usually pale orange. It's a variety of gracillar. Yeah. There's a bunch of other gem names for it. So some of those are varieties. And then again, there are more true minerals in the group. So let's see. Don't want to keep doing this forever here, but let me figure out how to. So here's where it starts getting more complex. Okay, so you all probably know about zeolite minerals. Zeolites are what we collect on North Table Mountain in the cavities and the lava flows. They look even more spectacular from India, where they occur in the lava flows there. And you know, there's a bunch of different zeolite minerals. And in fact, there again, just like with all mineral discoveries, there are more and more known every year. And the latest count is there are 103 different kinds of zeolite minerals. And in this, these are some of the more common ones that you may have heard of, probably have. In this case, they don't all exactly have the same parallel analogous chemical formula. You see the chemical formulas kind of jump all around, but they all mostly contain sodium and potassium, sodium and calcium and aluminum and silicon. The thing that makes zeolite distinctive, I think this is the only other crystal structure diagram I'm going to show, is they have a crystal structure where they have big holes in the crystal structure, which actually are interconnected so that ions or water or gases can move through the crystal. They're permeable to these things and lodge in those holes or replace elements that are there. And that's what makes zeolites useful as water softeners and water purifiers, and they can actually be used to remove smelly gases from waste materials. So because of this big hollow channel in their crystal structure, large molecules can fit in there, okay? And just, these are some of the most common zeolite minerals, again, couple that we see from India, mesylite and stilbite. These are, I think most of you have collected minerals on the Table Mountains. These are the three most common minerals found on North Table Mountain. They're all zeolites, thompsonite, chabazite, analcime. And you can see they have different crystal shapes. The thompsonite usually occurs in these radiating balls. So there's our nice group of 100 plus different minerals. So again, this makes it easier when you can group minerals, and if you can learn something about zeolite minerals, and now you've taken care of 100 whole minerals at one shot practically. You don't have to learn something new and different about every one. This, for the record, if I went to the MINDAT website, this is an alphabetical list of the first 20-some of the zeolite minerals. And you'll just take my word for it that the list goes on to 103. So one of the things this is where mineralogists are making our lives more complicated these days, okay? I showed you a picture. I'll go back to the last slide. So there's chabazite. It occurs in usually kind of distinctly looking kind of rhombohedral shaped crystals. It's often kind of a pale pink or something related to that. Well, it used to be that we could just refer to chabazite as chabazite, and that's a nice mineral name, and what's not to love, right? We get it on Table Mountain. Well, now it's been grouped into a group of minerals, and it's got a suffix added to it depending on which chemical element is most abundant in the chabazite. Now, the normal kind would be to have mostly calcium, but this classification doesn't tell you which one is more common. So we've got one with calcium, one with K for potassium, one with magnesium, one with sodium, one with strontium, and each of them gets counted as a separate mineral species. So the people who really like to divide things up, they don't like you to just talk about chabazite anymore. They want to know, well, which of the 5 species of chabazite is it? And of course, you need a chemical analysis to tell that, which most people don't have. So that's one of our things that's making minerals complicated these days, but they have truly learned that there's different kinds of chabazite, and some is rich in one element and some is rich in another. And it's the way nature is, so I guess we just have to live with it. But for practical purposes, when you collect minerals on Table Mountain and you see chabazite crystals, you just call it chabazite, and most people aren't going to question you. Okay. Oh, so turquoise. So finally getting back almost to the end here, finally getting back to turquoise, which, as I said, was kind of what we got me started on this. So turquoise is a mineral, slightly complicated chemistry, copper aluminum phosphate with hydroxyl ions and water molecules in it. It rarely occurs as crystals, but there's a few localities in the world, like one mainly in Virginia, Lynchburg, Virginia, where they get tiny little micro turquoise crystals. But usually it forms at low temperatures in sedimentary or volcanic rocks. So it just forms nodules or seams. So it has very low crystal symmetry, triclinic. And we think of turquoise as being a very nice blue color, okay? But I talked about having been in that shop in turquoise. And if you haven't been there, I know some of you have, it's a real hoot to visit. You can visit the rock shop part of it. And then if you pay, I think it's $2 or $3, you get to tour the mining museum, which goes on and has every imaginable kind of cutout, including cutouts of John Wayne, artifacts, anyway, pumps, mining equipment, etc., including some Cerrillos turquoise. And here are some turquoise from Cerrillos and a couple of other places in New Mexico. And as you can see in this pile, some of it is deeper blue than others. Some of it is more greenish. Okay. Some of it is fairly pale colored. This is actually a little specimen that I bought when we were there last month. But some traditional Cerrillos turquoise is very green, like these two. And this is where Ray DeMark got off saying that not all Cerrillos turquoise is really turquoise, because turquoise is actually a group of minerals, just like feldspars and some others. So here's our regular turquoise. And there's the chemical formula I gave before, copper, aluminum, phosphate with some H2O in various forms. So there's these other minerals that have basically the same crystal structure. One of them is a zinc end member instead of copper. Zinc doesn't give it the nice blue color that turquoise. So if you've got some zinc in your turquoise, it's going to be probably a duller, paler color. There's another one called planarite that has no, it just has the aluminum and phosphate, no copper or zinc or iron at all, or at least not much. So it's going to be paler colored. And then there's 2 that contain iron in different forms, and iron generally colors things greenish rather than a pure blue. So if your turquoise tends to those compositions, it's going to be greener rather than blue. And this probably applies to some of the cereose turquoise. That one means unnamed mineral. It's been approved by the International Mineralogical Association, but hasn't been given a name yet. So these are all considered separate minerals. And if your turquoise really has 1 atom of copper for every 6 atoms of aluminum, it would be bona fide turquoise. If it's paler colored or greenish colored and had more tends toward one of those, to a mineralogist, it would officially be planarite or faustite or whatever. So that's why the turquoise group is a little bit complicated. Now, once again, our nice deep blue turquoise, like when you see the turquoise from Kingman, Arizona, and Bisbee, Arizona, that mostly fits the ideal turquoise, and it's real bona fide turquoise. The others can be anything. Once again, that's minerals, that's nature, that's the way it is. I think I have 1 or 2 more slides. I will just do them real quick. As you might guess, the tourmaline group is another very complicated group of minerals. You probably know there are different kinds of tourmaline, and there's actually a total of 45 different tourmaline species now. They all have a pretty long chemical formula. Schorl is the name for black common tourmaline. There's a lot of places in Colorado where you can collect schorl. It has a lot of iron in it, which gives it its very black color. So it's not of any use as a gemstone. The colored gemmy tourmalines have always been called Elbaite, named after the island of Elba, where there were pegmatites with tourmaline. And you see here, there's very little iron in it. It contains lithium and aluminum. It contains a little bit of iron and a little bit of manganese, maybe a few traces of other things, and that's what gives it all the different colors. More recently, they realized that a lot of the tourmalines, the gem tourmalines from Madagascar, which are famous for their really complex color zoning, like here, this is a slice of Madagascar tourmaline right there, and it's way cool. It goes from intense purplish red to yellow, and you get greens and blues. It's a mineral that's related to Elbaite in that it contains lithium and not much iron, but it contains calcium instead of sodium. So that makes it a separate mineral. And again, you can look at them by color and you could guess as to what the real chemical composition is, but it really takes a chemical analysis to know. And like I said, these are 5 of the more common tourmalines, and there's 40 more beyond that. And then we have our variety, our gem variety names, for tourmaline, which are some of which at least are familiar to you. Rubellite has always been the name for pink tourmaline. The name for green tourmaline isn't used all that much, but verdolite is sometimes used. Indicolite for deep blue tourmaline, achrolite, which means no color, for colorless. And of course, I think we're all familiar with watermelon tourmaline, which is way cool. And 2 more mineral groups that I will mention quickly, if you can handle it, okay? So you probably heard of the amphiboles. They're what we call a group of rock-forming minerals. They're usually black, sometimes fibrous minerals, or else they occur in elongated crystals. They're all different kinds of amphiboles. Some that you may be familiar with, because they occur in a lot of our rocks and igneous and metamorphic rocks in Colorado, is hornblende. is an old time name. If you've collected minerals down by St. Peter's Dome in the Pikes Peak area, you know there are black crystals called riebeckite. That's another one of the amphibole minerals. White amphibole with very little iron is the mineral tremolite. And if it's got a little iron in it, it's the mineral actinolite. Jade is a variety of actinolite where the crystals are very well solidly intergrown and small and can take a good polish. So those are just 4 names, and the bad news is a lot of these aren't really accepted as single names anymore because they've been subdivided into 20-some different things. That's why we got over 200 different amphibole minerals. And once again, pity the poor mineral collector or mineralogist who's trying to understand these. This is one little sample of all the 209 different amphiboles. And here's the hornblende group, and you can have ferro-fairy fluoro hornblende and ferro-fairy hornblende without the fluoro, and it keeps going on and on. And the last one I'll mention, which is that crystal on my very first slide that I showed on the right, was a mineral in the pyrochlore group. And these are oxide minerals. A lot of them contain rare metals like niobium and tantalum. A lot of them are radioactive because they can contain uranium and thorium. They used to simply go by the name pyrochlore. If you look in our minerals, pardon me, drink of water. In our Minerals of Colorado book, you'll see pyrochlore, but pyrochlore has now been subdivided into 21 different minerals based on their chemistry. Just makes it more complex. So here are 2 minerals in this whole pyrochlore supergroup, they call it. One from the volcanic rocks in the Mar volcano at Lochersee, Germany. They simply identified this as something in the pyrochlore group, and this one and one of the other subfamilies in the microlite group. So I wasn't going to show you any more of those chemical formulas, but I'm just going to finish by going back to, once again, my favorite Golden Nature Guide to Rocks and Minerals, which has the basics but doesn't have all of these details, and now you know all the complex details. And since I'm running out of voice and getting hoarse, I'm going to wrap it up right there, and hope I didn't get you too bewildered, but thank you for listening.